Good day everyone. Welcome to Unit 5 Lecture 1 for CpE 2301 Logic Circuits and Design. Unit 5 is all about the sequential building blocks. Unit 5 generally covers registers and some of its common types like counters and shift registers. For Lecture 1, we shall focus on the following: the definition of a register, registers with parallel load, synchronous counters, counter design, and the 74193 synchronous up-down counter. To begin our discussion, let's first define what a register is. A register is a group of flip-flops, and each flip-flop is capable of storing one bit of information. So therefore, if we have an n-bit register, it means that it is capable of storing or holding n bits of binary information or data using n number of flip-flops. The diagram here shows an example of a register. It is a 4-bit register made up of 4 D flip-flops. The circuit is capable of holding or storing 4 bits of information as given by A0, A1, A2, and A3 when specific binary inputs are introduced in I0, I1, I2, and I3 together with the correct clock inputs to each of the 4 flip-flops. The R input here found on each flip-flop simply resets or clears the data stored on the flip-flops to 0. Here is another example of a register. It is a 4-bit register with parallel load. If we try to analyze what the circuit does, is it reflects the inputs I0, I1, I2, and I3 at the outputs A0, A1, A2, and A3 respectively when the load input is set to 1 here and the correct clock input is supplied to each of the 4 flip-flops. When the load input is 0, the outputs A0, A1, A2, and A3 will simply continuously output their current states or stored values. What parallel load does is introduce a set of inputs to the circuit simultaneously, just like what I0 to I3 does here, and in most cases it is done to specify a set of values on several flip-flops, just like in this circuit. Please take note of the term parallel load, for it will be often used in the succeeding discussions and lectures. As you can see in the 2 examples, they exhibit the basic characteristics of register, which is to store binary data using a group of flip-flops. These characteristics are exhibited regardless of the circuit functionality. So with that, it means that registers may come in several forms and types. One type of register is a counter. You might be quite familiar already with counters from the previous lectures and discussions about flip-flops. Counters will be discussed further in this unit. By definition, a counter is a register that goes through a predetermined sequence of binary states. Counters can be generally categorized into synchronous or asynchronous type. Asynchronous counters are also called ripple counters. Synchronous counter is a counter whose flip-flops are all triggered simultaneously by a common clock source. The counters you designed in the previous lectures are mostly, if not all, synchronous, since their flip-flops are all triggered by a single common clock source. An asynchronous counter, on the other hand, has flip-flops triggered one at a time and in succession. This means that the flip-flops of this type of counter are triggered not by the same clock source anymore. The asynchronous counters shall be discussed further in the next lecture. The circuit diagrams shown here are examples of synchronous counters. This circuit is a 4-bit synchronous binary counter. It simply counts from 0000 to 1111 at the A3 to A0 outputs and repeats. The count enable here simply activates the counting operation when 1 is inputted and stops counting when 0 is inputted. This circuit is a 4-bit up-down binary counter. It simply counts up at the A3 to A0 outputs when the up input here is triggered and counts down when the down input here is triggered. You will notice that all the flip-flops for both counters are triggered by a common clock source. This for this circuit and this for this circuit. That characteristic of having a common clock source for all flip-flops make these two counters synchronous counters. In this unit, we shall focus on the use of MSI or medium-scale integration chips or ICs in designing counters. Before we talk about an actual IC or integrated circuit, let us first discuss how most common counters work. We have here a block diagram of a 4-bit binary counter with parallel load IC. The counter counts from 0000 to 1111 and repeats the count starting back from 0000 after the last count of 1111. Again, remember that this is not yet an actual MSI IC, and we shall use this block diagram to explore some common functionalities and behaviors of counter ICs. This particular MSI counter operates according to these functions described by this table. We can see around the counter the pin assignments for its inputs and outputs. The A4 down to A1 are the 4-bit output of the counter, where A4 is the most significant bit and A1 is the least significant bit. This is where the 4-bit count can be seen. The I4 down to I1 here are the parallel load inputs to the counter, where I4 is the most significant bit and I1 is the least significant bit. This is where the count that we want to set the counter to is inputted. Again, these are your parallel loads. The carry out pin here is an output pin that only outputs 1 during the count overflow or during the transition between the last count 1111 and the starting count 0000. It outputs 0 at any other times. The CP pin here is the clock input pin, where the clock pulses needed for the counter operation are inputted. Load, count, and clear are input pins that control how the counter behaves. Now, if we look at the table here, we can see that when the input at the clear pin is 0, the count at the output A4 to A1 is reset or cleared. It is reset or cleared back to 0 regardless of what the inputs at CP, load, and count are. This means that the clear pin is active low or is triggered when an input of logic 0 is inputted to it. So when the input to clear is 1, it does not have any effect to the counter operation, just like the 3 operations here. As you can see, the clear input is 1. We can see here next that when load input is 0, count input is 0, there is no change in the count output since you are not triggering the load or the count input pins. Both pins need a 1 input to be triggered. Here next, we can see that when we have a 1 input to the load pin and a rising edge on the clock input is detected, as shown here by the upward pointing arrow, the counter loads the inputs on the parallel load input I4 to I1 to the counter and shows them at the output count. Remember that a rising edge on the clock input refers to the clock edge on the clock signal during the transition from low to high or 0 to 1. Lastly, we can see here that when we have a 1 input on the count pin, 0 input to the load pin, and a rising edge on the clock input is detected, the counter simply performs counting. Let's try designing some counters using the MSI chip. So here, let's try some examples. So the problem is construct the following modulo 6 counters according to the specified binary states. Modulo 6 means that the counters will go through 6 counts. So therefore, a modulo n counter will go through n number of counts. Here we are asked to construct counters that goes through 6 counts. For the first one, the binary states or counts are 0, 1, 2, 3, 4, 5. Next, 10, 11, 12, 13, 14, 15. And for the last item, 2, 3, 4, 5, 6, and 7. For the example A, the circuit looks like this. Here, the count input is set to 1 because we want the counter to perform the counting operation. The clear input is 1 because we do not want to clear the counter at any point during the counter operation of this implementation. The CP is simply supplied with clock pulses. The parallel load inputs are inputted with zeros. The load input is provided an input from this AND gate using the A3 and A2 outputs of the counter. The output of this AND gate will only be 1 when bits A3 and A2 are both 1. So when the circuit starts counting, it counts from 0, then 1, then 2, then 3, then 4, and then 5. When it reaches the count of 6, which is 0, 1, 1, 0, A3 and A2 will both be 1. So therefore, this AND gate will output 1, which will then trigger the load input and then load the parallel load inputs 0, 0, 0, 0 or binary 0 to the counter. When that happens, A3 and A2 will both be zeros again, and so the counting operation continues starting back at 0. Thus, the binary counts of 0, 1, 2, 3, 4, 5 shall keep on repeating. Remember that the count of 6 will not be shown at the counter output, because by the time the count becomes 6, the load input is automatically triggered here, thereby loading 0, 0, 0, 0 or binary 0 at the parallel inputs right away. Here we are only using A3 and A2 in checking for the count of 6 because at the counts of 0 until 5, A3 and A2 are never 1 at the same time. The count of 6 is the first time that both A3 and A2 are 1 at the same time. In some cases, the best way to check for a specific count is to check all the bits of the count. In this case, for example, to check a count of 6, you may include A4 and A1 and connect them both to inverters or NOT gates and include them as inputs to the AND gate here. In this way, you can be sure that you are exactly checking for the binary value 0, 1, 1, 0. Another possible implementation of this counter is this. Here the count input is still set to 1 because we want the counter to perform counting operation. The load input is 0 because we do not want to load any parallel load inputs to the counter at any point during the counting operation in this particular implementation. The CP is simply supplied with clock pulses. The parallel load inputs will not matter since we are not triggering the load input in this implementation. The clear input is provided an input from the NAND operation result of A3 and A2. The output of this NAND gate will only be 0 when bits A3 and A2 are 1. So when the circuit starts counting, it counts from 0, 1, 2, 3, 4, and then 5. When it reaches the count of 6, which is 0, 1, 1, 0, A3 and A2 will both be 1, and so therefore this NAND gate will output 0, which will then trigger the clear input, and then the counter output will be reset or cleared to 0 here. When that happens, A3 and A2 will both be zeros again, and so the counting operation continues starting back at 0, and thus the binary counts of 0, 1, 2, 3, 4, and 5 shall keep on repeating. Remember that the count of 6 will not be shown at the counter output because by the time the count becomes 6, the clear input is automatically triggered, thereby resetting or clearing the count output here to 0, 0, 0, 0 or binary 0 right away. Here, to have a count of 10 to 15, the count input is set to 1 because we want the counter to perform the counting operation. The clear input is 1 because we do not want to clear the counter at any point during the counting operation. The CP is simply supplied with clock pulses. The parallel load inputs are inputted with 1, 0, 1, 0 or binary 10. The load input is connected directly to the carry out output. So when the circuit starts counting, it counts from binary 10, then 11, then 12, then 13, then 14, and 15. Based on its natural behavior, the next count after 15 or 1111 is 0000. However, remember earlier that it was mentioned that during the count overflow or when the count transitions from 1111 or binary 15 back to 0000 or binary 0, in between those counts, the carry out output becomes 1 from its usual output, which is 0. When that happens, as the count transitions from 1111 back to 0000, the load input shall be triggered, thereby loading the binary count 1010 or binary 10 to the counter and shown at the output. The carry out output will be 0 again, and the counting operation continues starting back at 10. Thus, the binary counts of 10, 11, 12, 13, 14, and 15 shall keep on repeating. Here, to have a count of 2, 2, 7, the count input is set to 1 because we want the counter to perform the counting operation. The clear input is 1 because we do not want to clear the counter at any point during the counting operation. The CP is simply supplied with the clock pulses. The parallel loads are inputted with 0010 or binary 2. The load input is connected directly to A4. So when the circuit starts counting, it counts from binary 2, then 3, then 4, then 5, then 6, and then 7. When it reaches the count of 8, which is 1, 0, 0, 0, A4 will become 1. So therefore, it will then trigger the load input and then load the parallel load inputs 0010 or binary 2 to the counter and then shown at the output. When that happens, A4 will be 0 again, and so the counting operation continues, starting back at 2. Thus, the binary counts of 2, 3, 4, 5, 6, 7 shall keep on repeating. Remember that the count of 8 will not be shown at the counter output because by the time the count becomes 8, the load input is automatically triggered, thereby loading 0, 0, 1, 0 or binary 2 at the parallel input right away. Now we will try to use an actual counter chip or IC in designing some of the counters. In this discussion, we shall specifically talk about the 74LS193 or the presettable 4-bit binary up-down counter. From its name, you can see that it is capable of performing 4-bit counting, and its count could either be count up or count down. It is also presettable, which means we can specify the count at the counter output at any specific time. The table here summarizes its mode of operations. This is the block diagram for the 74LS193 counter. The pin assignments for the different inputs and outputs can be seen here. Take note of the VCC and ground pins, which are pins 16 and 8 respectively. The A, B, C, and D inputs here are the parallel load inputs to the counter, where A is the least significant bit and D is the most significant bit. The up input here is where you will connect the clock generator when you want the counter to count up. The DN input here is where you will connect the clock generator when you want the counter to count down. The load input here is what you trigger to load the parallel load inputs at A, B, C, and D to the counter. The CLR or reset is the input that you trigger if you want to reset or clear the count of the counter to 0. QA, QB, QC, and QD is where the output count is shown, where QA is the least significant bit and QD is the most significant bit. The CO or the carry out output is always 1 and only outputs 0 in between the counts of 1, 1, 1, 1 back to 0, 0, 0, 0 in a count up operation. The output BO or the borrow out output is always 1 and only outputs 0 in between the counts of 0, 0, 0, 0 back to 1, 1, 1, 1 in a countdown operation. Now let's look at the table again and the different operating modes of the 74LS193. First is the reset or clear operation. This operation resets or clears the count to 0, 0, 0, 0. To be able to do that, a high input or 1 should be supplied at the CLR input as shown here. And so then the outputs at QA, QB, QC, and QD will all be low or 0. Next mode of operation is the parallel load. This operation loads the parallel load inputs at A, B, C, and D to the counter and shows them at the outputs QA, QB, QC, and QD. To be able to do that, a low input or 0 should be supplied to the CLR input as shown here. And a low input or 0 should also be supplied to the load input as shown here. Next mode of operation is the count up operation. This operation makes the counter count up or in ascending order. To be able to do that, 0 should be supplied to the CLR, 1 should be supplied to load, and the DN inputs as well, and up should be connected to the clock generator. Take note that the rising edge or positive edge, as shown here by the upward pointing arrow, is what's detected for the count up to happen. The next mode of operation is the countdown operation. This operation makes the counter count down or in descending order. To be able to do that, 0 should be supplied to the CLR input, and 1 should be supplied to the load and up inputs. The clock generator should be connected to the DN input. A rising edge or positive edge on the clock input is detected by the counter to perform a down counting operation. It is shown here with this upward facing arrow. Let's now try to solve some counterexample problems for the 74LS193. Here, let's try to analyze what the output counts of this counter will be. This counter will count from 0 to 7 and then back to 0, then repeats. The pin names in Proteus might be different from what are shown here. You might encounter some other pin naming configurations when you use the Proteus software later on. But take note that their functionalities will remain the same. This is also true among various integrated circuit datasheets that you may encounter, as different IC manufacturers sometimes name the component pins differently, but still their functionalities remain the same. So now let's discuss the circuit operation. Again, the circuit counts from 0 to 7 and then repeats. The parallel inputs here have no effects because the load input is supplied with 1. The clock generator connected to the up input and the DN pin connected to high will cause this counter to count up. The CLR or the clear input is connected to the output QD of the counter. QD becomes 1 for the first time during the count of 8. So when the counter reaches the count of 8, you will not see it at the counter output anymore, because at that time the clear input has been triggered already, thus the counter resets back to 0 and then the counting continues. And so you will only see the counts 0, 1, 2, 3, 4, 5, 6, 7, and back to 0 again in this particular counter. Let's try to show the counter behavior in Proteus. So this is the circuit for the example. By the way, before I play the circuit, when using clock generators in Proteus, you may adjust the frequency of the clock generators to make the counting go faster or slower. You can do that by going to the component properties and changing the frequency value. Just like this. You can simply change the frequency values here. For this particular example, let's leave it at 1 Hz. So now let's see how the circuit behaves. So as you can see, the circuit simply counts from 0 to 7 and then repeats. So for the next example, let's try again to analyze what the output counts of this counter configuration will be. This counter will simply output 1001 here, or binary 9 continuously. That is because of this CO output connected to a NOT gate, and then the NOT gate output connected to the load input of the counter. Remember earlier, it was mentioned that CO is always 1 and only becomes 0 between the count of 1111 and 0000 during a count up operation. So therefore, when the circuit starts counting, the CO output here is 1 and then goes through an inverter or NOT gate and then becomes 0, and the output of the NOT gate is inputted to the load input. That will trigger the load operation and cause the counter to continuously load the 1001 input at the parallel load inputs. The other input pins here will have no significant effect to the counter behavior in this implementation. Let's try to show the counter behavior in Proteus. As you can see, the circuit just continuously outputs 1001 or binary 9 at the counter output. In the next examples, we shall be designing counters using the 74LS193 according to these specifications. For the first one, let's try to design a modulo 10 up counter that counts from 0 to 9 and then repeats. Let's go straight away to Proteus and show the circuit. The circuit looks like this. Here we can see that the parallel load inputs each have a 1 input, but these inputs have no significant effect to the counter since the load input here is attached to a 1 input, which means that it is not triggered. The up pin is attached to a clock generator and the down pin is attached to 1 input. Therefore, with this configuration, the counter counts up. When the counter starts counting, it starts from 0, and when the count reaches 10, the output here is 1, 0, 1, 0, or binary 10. Those outputs are checked by this combinational circuit such that when the output is 1, 0, 1, 0, or binary 10 and inputted here to this part of the circuit, this AND gate gives an output of 1, thereby triggering the clear or reset operation of the counter, and the count goes back to 0, and then the counting repeats. So therefore, we shall only see the count of 0 to 9 continuously, as you can see on these outputs. Let us show how item 3A here can be implemented differently. The circuit will look like this. Here, instead of checking all the 4-bit output of the counter, only these 2 bits, Q3 and Q1, are checked to see if the count output is already 10. Because in the entire up counting cycle of the 74LS193, it is at the count of 10 that these 2 pins would output 1 at the same time. And so we can use that case to check for a count output of 1, 0, 1, 0, or binary 10. So as you can see, the count output here still counts from 0 until 9. For the next example, let's try to design a modulo 11 down counter that counts from 10 to 0 and then repeats. The circuit in Proteus will look like this. Here we can see that the parallel load inputs have 1, 0, 1, 0, or binary 10 input. The DN pin is attached to a clock generator and the up pin is attached to a 1 input. Therefore, this counter counts down. The CLR or reset input here is attached to the ground, which means it is not triggered in this circuit. When the counter starts counting, it starts from 10, and when it reaches 0, its natural behavior is to go back to 1111 or binary 15 in a countdown operation. But if you recall earlier, it was mentioned that this pin, the borrow out, or sometimes called the TCD or terminal countdown pin, is always 1 and only becomes 0 when the count is between 0, 0, 0, 0 or binary 0 and 1111 or binary 15 during a countdown operation. This means that we can use this pin to trigger the load input after the last count of 0 in order to load these parallel load inputs to the counter and show them at the output. The count starts again at 10 and then repeats. So therefore, we shall only see the count of 10 down to 0 continuously, as you can see here on the outputs. For the next one, let's try to design an 8-bit up counter that counts from 0 to 255 and then repeats. Let's go to Proteus and look at the circuit. The circuit looks like this. So in this particular example, I simply just increased the frequency of the clock generator so that we can have the counter count faster. So in this example, I set the frequency to 10 Hertz. So here, we have two 74 LS193 to cover all the 8 bits of the counter. We then select this chip on the right to hold the 4 LSBs, and this chip on the left to hold the 4 MSBs. For all the 8 bits together, this is the LSB, or the least significant bit, and this is the MSB, or the most significant bit. Here we can see that the parallel load inputs for each chip have an input of 1, but these inputs have no significant effect to the counter, since their load inputs here and here are attached to a 1 input, which means that the parallel load is not triggered. The clear or reset inputs for both chips, just like here and here, are attached to the ground, which means they are not triggered in this circuit as well. The up pin of this chip is attached to a clock generator, and the up pin of this chip is attached to the carry out or terminal count up of this chip, and both their DN pins are attached to a 1 input. Therefore, both counters would count up. Their clocks are connected in such manner with respect to the clock generator because we want to trigger this chip first since it holds the 4 least significant bits, and only trigger this other chip when one full counting cycle of the first chip on the right occurs. With that, the counting will go from binary 0 to 255 continuously, as you can see on the outputs here. For the last example, let's try to design a 5-bit up counter which counts from 0 to 31 and then repeats. This time, a 74LS76 or JK flip-flop shall be used to cover 1 bit of the 5-bit counter. Let's now go to Proteus and show the circuit. The circuit will look like this. Here we have one 74LS193 that holds the 4 least significant bits of the 5-bit counter, and one 74LS76 that holds the 5th bit or the most significant bit of the 5-bit counter. Here we can see that the parallel load inputs for this chip each have a 1 input, but these inputs have no significant effect to the counter since their load input here is attached to a 1 input, which means that it's not triggered. Therefore, these will not be loaded to the counter. The clear or reset input is attached to the ground as seen here, which means it is not triggered in this circuit. The up pin of this chip is attached to a clock generator, and the DN pin is attached to a 1 input, so therefore this counter would count up. The JK flip-flop here is configured as a T flip-flop as shown here, with the inputs J and K connected to a 1 input signal. So that means this flip-flop will just continuously toggle between 0 and 1 whenever its clock here is triggered by the carry out output or the terminal count up output of the 74 LS193. A NOT gate is added here to delay the triggering of the JK flip-flop, since the JK flip-flop is a negative edge triggered flip-flop. With those configurations, this counter will just count according to the natural 4-bit counting and then trigger this JK flip-flop configured as a T flip-flop when one full counting cycle from 0 to 15 occurs. With that, the counting of all the 5 bits put together will just go from 0 to 31 continuously, as shown on these outputs. So that ends this lecture. Thank you for watching and listening, and have a good day.